And here we are. Hey, Thomas.
Hey, Luca.
After a while, there has been some uh, holiday time, some work in between offsites. So we haven't been so regular lately, but the work on Thunder has been proceeding like crazy. So today we're here to show the progress on a very fancy aspect of Thunder, which is transforms composition in right now like distributed is the theme of the day.
Yeah.
So yeah, so the goal that we already talked about a few episodes ago. So last episode was about autodiff as a transform. So how can you compute forward and backward, or the backward from the forward, just as a transform of the computation that your model does in forward, which gives you a lot of control on what the backward actually does, and you can look at it, which is not very usual as a capability, especially in PyTorch. And then the same aspect, the same concept of transforming a computation can be applied to distributed. And we already saw DDP, FSDP, where FSDP you shard the parameters and then right before the computation, or a few ops before the computation, but no later than when the matrix multiply needs to be executed. Of course, you gather all the parameters so that you have the full matrix. You can compute your matrix multiplication, and then you basically avoid storing all the weights in a single node. And DDP, on the other end, is simpler because you just provide different data to different copies of the models running on different GPUs. And then you end up computing the gradients and you synchronize the gradients in the end.
Right.
And so FSDP requires a lot of more communication. DDP, a lot less communication, but it forces you to hold all the model in a single GPU. And so what if we could mix the two and say, okay, we don't have to shard. If you have a lot of GPUs, you don't have to shard your model across all the GPUs. You just need to shard it across the GPUs that will be sufficient to hold your model in memory. And then adopt the DDP philosophy to just communicate as little as possible across the other groups of nodes. And so maybe we can draw this and make it easier for everyone. Let's see here. All right. So let's say that we have like four machines, or four GPUs, or four of anything.
And so one thing that has been fun, that you know that Jensen predicted you couldn't give H100s away once the B200s hit the market.
Yep.
And it seems to have been true, right? So we have the first B200s on the Lightning platform, and H100s are super available now, right? So those are four H100s right there.
Because you can just get them. Great.
Right.
So you have a Lightning H100 here, and H100 here, and so on and so forth. So you can think about this as individual machines with one GPU each. You can think about this as four GPUs on the same machine, so it doesn't matter. All it matters is that you have a resource with a process, and the process is kind of isolated, needs to communicate its weight or whatever they are to the others in order to compute. And let's say you have a model, and your model fits two GPUs. All right. So you can actually, meaning it doesn't fit to a single one. So you cannot load it on a single H100, but two H100s are enough. And so if you shard the parameters of the model into two portions and store one here and one here, and one here, then your model fits in memory. So say this holds this leftmost part of the weights, and this will hold the rightmost.
in practice, you have more for the training. At least you have more than the weights, right? You have the weights, the gradients, the optimizer state, all this stuff.
Yeah. So you have weights, you have gradients.
You can chart all of them.
Activations, optimizer steps, or optimizer parameters. Okay, so all these, and these are fairly large typically. And then you can shard the whole thing. If you only shard weights, you can only shard weights. You can shard weights and gradients, and you can shard weights and everything else. And this goes with 01, 02, 03 type of sharding. But ultimately, you have stuff you need to keep in memory, like here, and you can just distribute them. And then, does this mean that we compute matrix multiplications in a sharded state? No, because right before, and we already touched that, right before computing a matrix multiplication, for example, just is one of the things you can compute, each node will say we are in the leftmost node here, and will right before computing the getting to the computation, or n steps before, if you have enough memory, you can gather the parameters that you're missing, so you have a full matrix. You can compute the matrix just as it's written on your model, and compute the result, and then destroy or deallocate the portion that you gathered. And so this is a lot of communication back and forth between these two machines, right? Because they need to exchange stuff all the time. Right. The good thing is that you can overlap communication and computation, so you can gather all the things that you need together to perform the computation well in advance to when the computation happens. And so you're not left waiting while you're communicating in order for you to matrix multiply things. But say you can just store it in 2 and you have 4 nodes or 4 computing units. Well, what you could do there is avoid communicating, do a lot of sharding very granularly and communicate across all the nodes. So you don't want to do this if you don't have to, of course. But you could say, okay, what if I could just do exactly the same here, right?
Yeah.
And so that these two can still communicate and request things just like the first 2 nodes, but between these, we're only synchronizing the gradients.
Yeah, and only the dotted gradients, right?
Yeah, only the dotted parts. Yeah, here and here. The gradients relative to this shard. And this happens at the end, like when you do forward, backward, optimizer step, then at optimizer step is where you want the gradients to be all the same across all machines, so that the result of the optimizer step applying gradients to the weights somehow in its own way that the particular optimizer wants to do it, then you will find yourself with weights that are the same, because you apply the same gradients to the same weights to obtain a new version of weights that is all the same. And all you need to communicate in this case is the gradients. So you need to accumulate the gradients and so that they are the same across all the DDP replicas, and then apply them. And you can do that across this column and across this column. All right. So right now we have basically a matrix of nodes. On the horizontal, we shard, and on the vertical, we just exchange the gradients at the optimizer step. And of course, you can be creative with this. Now, if you have this mechanism, now you have a very large cluster of machine, a lot of GPUs. And then if the GPUs are, like, say you have 8 H100 node and another 8 H100 node. Sorry, I'm drawing terribly here. And you shard the model across 16 GPUs. And now you have a lot of these pairs of nodes here. You can apply exactly the same concept, right? Or you can also shard across more and so on. So this is kind of a mini model of this situation. If it works with this, it works with more complicated stuff. Is it convenient for you to do so? It depends on the topology of your cluster. But the fact that you can make these trade-offs is very powerful. And in our world, what we want to do again is have our NN module, Thunder, compile it, get a trace out, apply transforms, and one transform will apply. What's the first, DDP or FSDP?
The first will be FSDP because it's the innermost.
Oh yeah, for sure. Yeah, because of course you need to first shard and then do add the synchronizations on top of this, of course. And then so this is a transform. And then you can apply the other transform, which will add the DDP dimension to it. And now your model is FSDP plus DDP. And in the future, you could throw tensor parallelism in there. So that's what we're building, the ability to compose distributed transforms on top of a model that is written for a single GPU. All right. So that's the program for today. Now on to you, Thomas.
Now we need to see it, right?
Yep.
So Luca draws artfully, and I believe everything he shows us, but let's see if we can.
This is easy
because
it doesn't need to work. Yeah.
See things, right? Okay, so here we have the window, and I'm on a 4 H100 machine here, which are like super cool, and I'll stop and because I didn't want to have interruptible for the podcast, I took the expensive one, but you can even save half by taking an interruptible one if you can cope with it. But so I have a 4 GPU node here, and usually you start these things with torch run or some helper, but here I do it manually for us. So let's do it. And one nifty thing that PyTorch added is it has introduced the concept of a device mesh. So before, when we did distributed, we always had the process group, and now and we saw in Luca's pictures that there were like 4 groups of processes that interacted along the edges of the square of nodes. And so the device mesh is a multidimensional thing where you get slices that are the process groups. And so we have a 2x2 device mesh from our 4 GPUs. And one of the dimensions will be DDP and the other will be FSDP. And so
this is really cool that Torch introduced this. This is not tied to anything but the process groups. It's a way to set up process groups so that it doesn't get crazy. It's easily manageable, and we'll see how that's done.
And the drawback of not having some helper is, of course, that I can make a fool out of myself trying to run it all manually. But so here we are. And now the initialization succeeded. And we see that here we are at global rank 0, FSDP rank 0. We can print the device mesh. It has like 4 nodes organized in a 2x2 array. And my mesh coordinate here is 0, 0. And similarly, I have 0, 1 here, 1, 0, and the global rank 3 has the coordinate 1, 1.
Yeah. So now think about Yeah, sorry.
No, no.
Just I want, because not everyone is used to initializing these processes manually. So what this did, if you scroll up, all these environment variables, let's go through them really quickly, one by one. Master address is localhost. It can be your node that is your rank 0, where everybody refers to. And the master port is the port where they interact. And then where the backend interacts. So you can have nickel or glue as a backend. It doesn't matter. It's just the port where the network communication happens. Then the world size is the amount of machine or amount of processes, not the amount of machines, because you will have like 4 in the same machine. So the amount of processes, and typically one process maps onto the single GPU. Local rank is what am I on the machine, and rank is what am I across the world size. And it's just an index that goes from 0 to the world size. The rank. The local rank will be 0 to the number of devices or processes on a single machine. Yeah, that's it. And so by initializing these and initializing the device mesh, then each process that is running on the same notebook, but each process will have its own position in this 2x2 square that we draw. And this is how it knows about itself from the environment variables. That's it.
Yeah, and I can like index it with these, either with dimensions or with the DDP dimension. And so it automatically knows the index, and I just need to say I want the DDP one, and then I get just the DDP slice, and this now is between the 0th and the 2nd node, which are the left 2 nodes in the drawing that Luca showed, right?
The vertical.
And so we can take a model, and I'm not like a super fancy person when I build these little things, and I want to convert this very example into a test. So we just built a 2-layer MLP here for laughs, and then we just write the transforms, and the transforms both take a process group. And so for one, I did take the FSDP process group, and for the other, I take the DDP process group. And then I have these two transforms, and I just run the model just like I would. And why do I put imp here instead of imp sharded? I don't know. But yeah. And then I run through it, and I can check whether I compute the same thing if I do the unsharded vanilla model here, or if I do the sharded model. And let's try how this goes. And I need to run it on all 4 of them because they need to process in the sync.
And they will wait for each other. So
right. And so you see that it printed evil hack on one of those. And now does it work, or did I do something wrong? So this is still running. Still running. Still running. I think I did something wrong with the running. Sometimes it can be a bit like, if I do this manually, I sometimes lose, and it seems that I did something wrong. So let's redo it, and I need to stop it for all of them.
You want to restart the kernels as well, maybe?
Yeah, I need to restart the kernels first, and then I can run it again, because I need to deinitialize the distributed completely.
Yeah. Or distributed is usually very stiff. Like
right.
Yeah, it doesn't let you fool around too much. It expects to be initialized statically. It expects the programs to be exactly the same program. So it will get confused very easily. So don't do this at home, or do it at home where if you need to understand things or hack around things, but usually this is something you launch with a launcher.
Right.
Yeah.
Okay, so now let's see. And it worked on all of them, right? So
yeah.
I
Probably it timed out. Probably something timed out because you waited too long before.
Yeah.
Yeah.
That's what we get for chatting. So if you train large LLMs, don't have a step where they don't do anything and you chat, because that will burn you. But so, of course, with the Thunder way, we can also do the look at the last traces. So Thunder last traces.
Yeah. So maybe we can mention also in fact what computed. So we computed the gradients, right? And then
so
go ahead.
we computed the forward and then the backward, and we looked at the slicing here. Because of the FSDP, every tensor gets split into two halves. And so we compared the gradient to the gradient of the reference, the correct slice here from the FSDP rank.
Yeah, perfect.
Which is what we expect, right?
Yeah.
And if we look at the program, now this is the forward is a bit simpler than the backward. And what happens is that the FSDP needs to gather all the parts from the weight. So this is the all gather prim implementation. And we have one here for all the weights. And then we need to wait for the data to arrive for the first layer, compute the first layer. We fuse here the ReLU, and then we have the second layer, and that's it. And here we see that we save some intermediate tensors, but hopefully not the gathered tensors, right? So 32 is the gathered tensor. This is not it's the activations that we save, right? Or the input.
For the backward, of course. Yeah. And then when you gather, it's also something you can play with. With a very large model, you don't want to gather at the beginning of the computation trace because you will run out of memory. So you want to do it block by block or with whatever. But now it gets very easy to understand where you are and where the trace is. You can reason about that.
And then the backward is the thing where both the FSDP and the DDP happen, right? Because we need to sync the gradients as well. So if we look at the backward trace here, we have, it's more elaborate, but we have the reduce scatter. And this takes the full gradient that I computed locally and divides it between the various nodes, right?
Yep.
And then we, after the scatter towards the end, we also have the all reduce, and this collects all and the all reduce. And now I promised to have I didn't merge the local branch. The all reduce takes all the gradients. This is the DDP. It takes all the slices that one set of corresponding FSDP nodes gathered and sends everything to everyone in this group to get the gradients for the full gradients for the slice across the DDP.
Yeah. It was the vertical arrows before in the drawing.
Right. And so one thing you noticed is that there's an output evil hack in between. And the thing here is that usually for DDP, it is useful to not send those tensors all individually, but to pack them up into one larger. And this is a bit that doesn't quite work yet. But yeah, we will make it work probably very soon. The other thing is, while debugging this, it has been useful here. You have a distributed reduce ops, and this is a enum value. And so you can in the new versions of Thunder, once I merge main into this branch, you can see actually distributed reduce ops sum. So this is one thing I like about these large transforms. We had Autograd, the Autodiff transform. We have now here the distributed transforms. You really find what the tooling should be. And so I guess the next things in Thunder will be just that, do the tooling from all the learnings we have so that the future transforms will be even easier.
Yeah, and sometimes you don't want to reduce the gradients. For example, when you do, sorry, it escapes me. Yeah, I have strong allergies, so I took my medicine, and now I'm even slower than usual. The micro batching, right?
Yeah, I mean, sometimes you can like collect a few gradients and then only sync every now and then because it's really a long time between them. Yeah, but so this is what I wanted to show.
Nice. So this is great. Right now we start seeing the power of layering transformations together, and we already layered the Autodiff, right? Because this also uses that in the back, and we'll be consolidating this, adding more, and I think we're proceeding towards making distributed very hackable, and that is really important for leveraging all the stuff that is landing also in PyTorch. For example, the different memory pools to communicate different things with different speeds across different networks. And doing that correctly is hard, and you need to be an expert. And so we hope that we can take all that expert level optimizations and stick them into a transform so users can benefit those things without necessarily become distributed experts. And that's the ultimate goal. All right. So this was great. Short but intense. So I hope we can see this in Thunder main really super shortly. And next on to the next transform.
Yeah, super good. So
bye,
you
Thomas.
have a great weekend.
Yeah,
and
you too.
See you soon.
See you soon. Bye-bye.